Okay, thank you everyone for joining. Um, Today we're going to be covering EIGRP, kind of a 101, 201 sort of course. If you do have questions, by the way, go ahead and put up your hands. I will do my best to stop and ask the questions in real time. Ben, I see you've got your hand up. I think that's probably up from before. Or did you have a question currently? Yeah, okay, perfect. So I will do my best to pay attention. Also, you can put something in chat. I will go ahead and pay attention over there as well. If I do miss a question at the very end, we'll come in and grab any questions that I missed. But feel free to ask as we go. So just a real quick look at the agenda. We'll have a quick intro to what SCUG is as we kick off the 2024 year. We'll go over the protocol in general, then we'll talk about the neighbor process. We'll spend a good amount of time over on distance, feasibility, and successors and some of those concepts. We'll also spend a decent amount of time over on the query process, which is important to the scalability of EIGRP. And then we'll end with some named versus classic EIGRP, or sometimes named versus numbered EIGRP. Classic and numbered are kind of the same concept. Conclusion. And then you will all get homework today. No one has to do it because I'm not grading it, but I included a little EIGRP quiz just to make sure you actually got something out of the session, right? So that you feel like, I guess I could say you get your money's worth, except it's a free user group, so you always get your money's worth in that sense, right? But it does cost your time, and I want you to feel like you learned something from it. So, introduction. Well, first of all, just welcome to, for those who might be new, the 25th year of the SoCal Cisco user group. We started in July, technically in June of 1999, but really our first public meeting was July of 1999. I was there in July. The June one was actually just the three people who had originally started it, none of whom have been with the group for many, many years. Most of them left that first year. Anyway, but I've been around since really the first public meeting. We have covered a lot of topics over those 2.5 decades. You can find some of the most recent ones up on our YouTube channel. Anyone who RSVPs for the event, I will send them a copy of the slide deck. And then when we get this up on YouTube, you also get a link to the YouTube if you'd like. And even if you can't make it or if you have to drop early, I understand, we all work in these kind of operational settings. You'll still have full access to the material, right? So just be aware of that. Also, if there is a topic that you would like to see, just let me know. Be aware, of course, I cannot present on every single topic. I'm I only have so many cycles and I only know so many things. So I may need to find a speaker or something, but I don't mind doing that. Also be aware, if it's a very specialized or highly esoteric topic, we may not even be able to find a speaker, or we may not have a large enough audience to support something like that, a topic like that. But by all means, just let me know. I'll put my, well, you'll get my email when I send out the slides and everything. You can just email it to me. You can also put it in the chat, and I will do my best to pay attention to that. And even though I do work for a Cisco Gold partner, LA Networks, I've been at LA Networks for over 20 years. Not quite as long as I've been with the Cisco user group, but almost. This is a very vendor neutral user group. You're not, we're not pushing anything or selling anything other than we're pushing engineers working with each other to get better in our skills, right? That's all. That's always been the point of the group. That will always be, as long as I'm involved in it, the point of the group. It's never been a marketing thing. So just so you know. So let's dive right in. So what is EIGRP? Let's have a quick overview. Well, EIGRP is a distance vector routing protocol, right? Sometimes you hear the phrase that it's a hybrid protocol, and I understand why they say that because it does have some features that other distance vector protocols like RIP don't have, but in truth, it is just a distance vector routing protocol. I like to think of distance vector protocols. I like the phrase routing by rumor. Basically, your neighbor, you form a neighbor relationship. Your neighbor tells you, hey, here's all these networks I can get to. You don't do anything to verify them. You don't do anything to build out anything. You just say, okay, those are all your networks. Let me take those, add my networks to them, and then I'll send it to my neighbor down the way that I also have a relationship with. So that's why they call it routing by rumor sometimes is it's kind of a spray and pray sort of approach to networking, right? You just tell your neighbor, here's all of the things I can do. Um, and when you want to separate internal versus external routes in EIGRP, meaning what was created through a network statement versus say what was created when you redistributed some routes, whether they're statics or whether they're um, from another protocol like BGP or something like that. EIGRP uses administrative distance. So an internal route has an AD of 90, an external route has an AD of 170. I'm not a huge fan of this method, but it's important, really, in my opinion, right? And I'm a router person from way back. Um, it's important to understand how any protocol deals with internal versus external routes. And EIGRP uses administrative distance. Not my favorite method. It's kind of to me, a inelegant tool, but you know what? It works, and as long as you understand it, then you can plan for it and you can deal with it, right? Um, it, by default, at a simple level, we'll get into the non-simple stuff, of course, but at a simple level, it's just a two-factor metric. It's just whatever the lowest bandwidth is along the path, and then the sum of the various interface delays along the path, right? And we're going to touch on that a few more times, right? Lowest bandwidth, sum of the delays. There is an actual metric. This really isn't the formula. This is a simplified version of the formula, but it's basically 256 times 10 to the 7th divided by that minimum bandwidth number plus the total delay divided by 10. And like I said, this isn't really the full formula because there are other components to the metric. Namely, that you could have load, reliability, and MTU. However, by default, those are just multiplied by 0, and so they're dropped out of that calculation. And that's why a lot of times you'll see that it just gets simplified to this 256 times 10 to the 7th divided by the minimum bandwidth plus the total delay divided by 10. So if you're joining a little bit late, just so you know, if you have any questions, please just put up your hand. I'll do my best, or put them in chat, and I'll do my best to follow them up there. Anything I don't get to in real time, I will get to at the end. So, and I should mention right at the get-go here, I tend not to, I don't present in a way to help people get certifications and stuff like that. I have certifications. I am a CCAE. However, that being said, that's not really how I treat it. And so I will say things like, EIGRP, it's a two-factor metric. It's just the lowest bandwidth and the sum of the delays. That's a true statement. It's not like I'm lying in some way. I'm not falsifying anything there. But as you can tell, there is more to it than that. I mean, number one, it could be a lot more than a two-factor metric, right? You could use load, reliability, and MTU. Also, there is a hop component to it in that EIGRP cannot have more than 100 hops in a prefix. I can't imagine an EIGRP network that has 100 hops within a single AS, but technically that's a true statement. So Let's talk about the advantages of EIGRP. It has two big advantages. Number one, it is fast. It will be about the fastest routing protocol you could ever use. It does that by something called the dual algorithm. Also, besides just being fast, it is very simple to deploy, or at least it can be very simple. We're going to touch into when it doesn't get simple. However, if you had a small network, just a couple of sites maybe, and you wanted to use dynamic routing between them, EIGRP is a nice option in that it's very fast. It takes a second or less just out of the box. You can tweak it down to about 100 milliseconds to propagate changes in a small network, even in a large network, to be honest. But it takes a lot more work to do that. It's just so fast. And if you had a small network, you don't have to do it. It's not like OSPF where you have to enforce some kind of hierarchical design from day one, right? It can be very, very simple. So, I mentioned EIGRP is fast, and I said that's because of the dual algorithm. That stands for diffusing update algorithm. It's basically a way to flood the changes pervasively, right? And to be aware, it is good at it's flooding the changes technically. Now, of course, when you first bring up an adjacency, everything's a change, so you flood the whole route table that you have access to. But after that, what it's really flooding are the additions and the withdrawals. So it's partial updates, which isn't common in distance vector protocols, although distance vector protocols aren't all that common themselves anymore. But that's why it's so fast, because it floods it out all those interfaces, and then it gets flooded out all those interfaces on its neighbors, and then it just trickles on down so that your routes go really quick. The other thing that makes it fast, we'll talk about a little bit later, deals with the concept of feasible successors. We'll talk about that in a few slides. Every advantage comes with disadvantages, right? So there are some disadvantages. The number one disadvantage in my mind is that it is a distance vector, which makes it kind of inherently a little less trustworthy. I definitely am a little bit of a preference towards link state protocols, or BGP, which is not really link state or distance vector. And it does have proprietary origins. Now, this is a common misconception these days that EIGRP is proprietary. There's actually an RFC. It's been released to the public. Anyone can use EIGRP. It's not Cisco proprietary any longer. However, the reality is that they did that move a little too little, a little too late sort of thing. And so while it's not technically proprietary any longer, for the most part, no one uses it except Cisco. So it's not proprietary any longer, but it does have proprietary origins, and it makes it more or less proprietary these days by default. And we'll talk about this a little bit more. But if you want to scale EIGRP up to large networks, which you can do, that is definitely possible, you will lose the simplicity factor, right? You'll have to discard simplicity for scalability, which is why I mentioned it's really great for smaller environments because it's fast, it's simple. You don't need to go consult the CCNA Jedi Council for design to deploy it or anything. You can just turn it on, put in your network statements, and walk away, and it will pretty much just work, and it will work super quick. Let's break into that metric a little more. Let me just check and see. I don't see any questions. Okay. So I'm not going to keep reading out the equation, of course. The default metric is what we had up before, and it's here again. There are 5 what we call K values associated with EIGRP, and they're technically, the values are not the bandwidth, the load, the delay, the reliability, and the MTU. Rather, they're the multipliers, right? It's really what we multiply the bandwidth, the load, the delay, the reliability, and the MTU by. So K1 through K5 can vary in value from 1 to 128, actually technically 0 to 128. Only bandwidth and delay are really used by default, as I mentioned, and their K values are 1, meaning what this really is 10 to the 7th divided by 1 times the minimum bandwidth. Since 1 times something is just that something, we just drop the 1 value and we just say, it's just reading the minimum bandwidth, right? Just like it's total delay multiplied by 1 again, that would just be the total delay, so we just write it as total delay, right? And then the load, the reliability, and the MTU are zeroed out. Those K values are 0, so they just get dropped from the equation. So again, to me, it's if you're going to cert up, you need to know how this is actually calculated. You need to know how to mess around with these K values and what those implications are. However, if you're being practical minded, which I often am, really just remember it's the lowest bandwidth in the cumulative delay, right? And remember, it's not the total bandwidth. It's only the minimum bandwidth, right? Whatever the lowest bandwidth is along a path, that's what you're using, not the total bandwidth. And because of that, if you do need to tweak the metrics, I would not do it with bandwidth. I would do it with delay. If you do it with bandwidth, there's a couple of problems, but one of them right off is that's a real global change because I've changed it since I only care about the minimum bandwidth. I've changed that for all routes that go through that router, right? Whereas delay, I'm really tweaking that interface. Now it is cumulative delay, so yes, it does trickle down for sure. It's just a much smaller trickle down type of effect. We'll talk about another way to tweak metrics as well coming up here. And while, again, if you're going to cert up or something, it's important to understand these K values and really know the entire formula. They're zeroed out for a reason. I would recommend that you do not use the other K values. Don't use load, reliability, and MTU. In fact, PAC will tell you, please don't use these. Go to like a Cisco Live and go to an EIGRP design session. They'll tell you, please don't use these. In the quote unquote old days, when I was first starting out, I actually started before EIGRP was a protocol. But when I first started using EIGRP back in the 90s, it was strongly recommended that you not use it because it could really make your router unstable because it didn't really have the processing horsepower. These days, we can totally use them. We have the processing horsepower. You just may find that you get instability if you start doing it. Unless you have a great reason, I would not use those other K values. I just check any questions. I don't see any hands up, so I think we're good. Let's talk about another way to alter or affect metric or cost, right? And that's the offset list. This is actually my preferred way, typically. Depends a little bit on your use case. You could do things, again, through delay or bandwidth in that order, in my opinion, right? But those are more or less global options which could affect at least potentially all of EIGRP. We could also manipulate EIGRP on a per prefix basis, right? And I have a sample scenario. This isn't the only scenario, it's just a sample. Let's say that we have two routers, R1 and R2. They're both originating a default route. However, we always want everyone to prefer R1 for the default, unless for some reason R1's default goes away. And then I want you to take R2. And then if R1 comes back, I want you to go back to R1. And I want that all to happen kind of automatically so I don't get called in the middle of the night saying that R1 lost its default. Can you set something up? This is a perfect use case of when offset list becomes handy because offset list allows us to match on an ACL and then just add extra cost to just that single prefix. Now I say a single prefix, but since I'm matching on an ACL, I could also match on multiple prefixes. In my example, it's a single prefix, which is the quad 0, right? And then here you can see an example of how I do this, right? I just set up my access list, offset default, permit the quad 0, and then I go into EIGRP and I set up an offset list and I call my access list and then I say whatever my metric is. Here I've picked 1,000 just because that's a nice round number. You can pick any, well, not any number you want, but pretty much any number you want and it will work. And like I said, in the slide, I say, we could do this on a single prefix, but keep in mind, you could just as easily match all routes, right? If your network utilizes the 10.0.0.0/8 address space, for example, you could just as easily set that access list to all your 10.0.0/8 routes, right? And affect the same. So let's say you had two links. One was connected to the internet, the other one was connected to LTE. The LTE comes with a cost. I have to pay per gigabyte that I consume or something like that. So maybe I want to keep a routing adjacency, which costs me next to nothing, but I only want to fail over to that LTE link if my DIA link goes down. This could be a nice way to do something like that, right? So let's talk a little bit about the neighbor process. There's really just a couple of things that are required for two routers to become neighbors. You have to have a network in common, right? You can't become neighbors, generally speaking. This is different in BGP, but in most interior protocols, you cannot become neighbors unless you have a common network, a wire in between those two, a directly connected interface that you share, right? Your autonomous system number must match, or your autonomous system must match, I should say. And then you need to agree on the metric composition. I can't have one router that's paying attention to K1 and K3, which are the default K values that we pay attention to. That's basically bandwidth and delay. And then another neighbor that's also throwing load into the mix, right? If you do that, they will not form up because they can't agree on how to determine a metric. And lastly, they have to be able to exchange hellos. I can't have like a layer 2 firewall or something in between that might be dropping hello packets or something like that. As long as they can exchange hellos, they can agree on what makes the metric up. They have the same AS and they have a directly connected network between them. They will form an adjacency. Now, these are the minimums. You could have something like authentication, and then obviously your authentication also has to match, right? But these are kind of your minimums, right? Oops, sorry about that. And as long as you meet those minimums, you're going to be able to form an adjacency just fine. I put this in that kind of, it's important to know how to do these things or what these processes look like in any protocol you're going to work with. So that's why it's up here at the beginning. So let's maybe take a look at how EIGRP works. I have a very simple small lab set up. And my lab kind of just looks like this. I just have R1 and R2. I've got some loopbacks on R1. I've got some loopbacks on R2. And then I've got a directly connected link in between them, right? So if we come in here, maybe we want to come to R1 first, show IP interface brief. you can see that I've got everything set up here. You can kind of ignore the G04 interface. That's what I'm using to get my out of band effectively set up. So we're really looking at those loopbacks and then my G00 interface. Same thing over here, right? You can see that I've got that set up. However, I don't have any routing yet. Right, I don't have, it turns out actually if I do show run, pipe it to this section of EIGRP, you'll see I don't even have EIGRP configured, right? So let's go ahead and configure that. If I come in and I do router EIGRP 100, I'm a fan of router IDs, so I'll come in and give it a router ID as well. And then I give it some network statements. I'm a big fan of proper inverse masking as well. Yeah, there's a question. Router ID is locally significant. Yeah, that's pretty much true. Yeah. It is used in the neighbor process, but you know, in EIGRP, it's not as critical as it is in OSPF, and it's not as critical in either as it is in BGP. I just find it to be a good best practice. Good question, Sahil. Oh, and then we better do it on our link, right? Okay. We'll have to do the same thing, of course, on R2. And to show you just how fast EIGRP is, I'm going to try to do this as quickly as I can. We need to do the directly connected link here. And I come out, and once again, I do my neighbor. And you can see my neighbor's already been up for 2 seconds. And I did that as fast as I could. I control Z'd out, and I just up arrowed twice to do the neighbors. And you can see I was already up and running, right? And sure enough, if I do a show IP route now, maybe I should do that for EIGRP just to make it simpler to look at. You can see I'm learning all those routes. Like I said, very fast, very simple, right? It's a great protocol for those smaller networks. And I say that, it doesn't mean I'm saying you shouldn't use it in larger networks. We're going to get into that. Just you're going to lose some of the simplicity when you go to the larger networks. You're going to have to make it hierarchical the same way we would do as OSPF, right? So, but it's that simple. Also, some other commands that I find very helpful. I love the command show IP EIGRP neighbor, which shows me how many neighbor, here, of course, I just have a single neighbor relationship, but it shows me how many neighbor relationships I have. So I like to capture these things before I make operational changes to make sure if I had 4 neighbors before a change, I still have 4 neighbors after a change, right? Just good best practices. Show IP protocol. If you're wondering about those things like the K values and you're playing around with those, And then you notice after playing around with them, especially in a lab or something like that, why is my EIGRP not coming up? Come in and take a look at those K values. Did I weight my metrics differently, right? You can see K1 is equal to 1, K3 is equal to 1, everything else is equal to 0, which is the default, as we've talked about. But if you were playing around with those K values and K2 was listed as 1, but if I came over here and did the same thing, show IP protocol, and over here, K2 is equal to 2, well, that's why your adjacency isn't coming up, right? We'll get into this a little bit more later on, but there is a topology table as well, right? And we'll talk about that. The topology table comes in pretty handy later on. Any questions? I don't see anything here. So I think we're good. Come back to the slides. Okay, let's start talking about distance, feasibility, and successors and how those play. This is where EIGRP starts getting a little more complex. Obviously mathematically it's already been a little complex. You think that's complex mathematically? Wait until we get into the named section of EIGRP, because it's really complex then. But let's talk about these concepts, right? There's a concept of reported, or sometimes the advertised distance. I do not like advertised distance because it gets abbreviated to AD, which to me is always administrative distance. So I will always refer to it as the reported distance. And basically the reported distance to a particular network is the cost to get there before I add my own cost, right? So from R2's perspective, to get to this 10.1.1.0/24 network, notice I'm not doing bandwidth and delay here. I'm just telling you what the cost is. R2, the reported distance is going to be 1,000 because his cost to get to R1 is 5,000. I don't add that to the reported distance, right? R3's reported distance would be 1,000 plus 5,000 or 6,000. Again, I don't add R3's cost. That's the feasible distance. The feasible distance is the cost to get to that particular network, including my cost, right? So R2's feasible distance is 6,000. R3's feasible distance is 11,000. And you may think like, do I even care? Well, it depends. But if we're going to get a little more advanced with EIGRP, then absolutely we care. And we're going to come into some use cases a little bit later when we get into things like the feasibility condition and variance, where these are important considerations, right? So just remember there is these two distances that we kind of think about: the reported distance, which is basically the cost for me to get to a particular prefix, not including my own cost, and then the feasible distance, which is my total cost to get to a network. Any questions? See anything? Perfect. As I mentioned and just kind of demonstrated just a second ago, EIGRP does keep a topology table. And there could be a lot of things in there, but two things that are of particular interest are concepts known as successor routes and feasible successor routes. A successor route is quite straightforward. That's the route with the best cost, right? It's whatever my best route to a particular path is, okay? So a successor route is the route I'm going to use. You can always have more than a single successor route, in which case EIGRP will just load balance them, right? A feasible successor is basically an alternative route. It's not the best route, but it's a, let's call it good enough route to keep it in the topology table. I will not use it. There's a way around this. We're going to get to the caveats in a few slides. But by default, I will not use a feasible successor. However, if the successor route goes away, I can just install the feasible successor right away. which again leads to that very fast convergence, right? It's instantaneous. We're talking probably in the microseconds, maybe as fast as a millisecond, but really it's so quick. It really comes down to how quick do you detect the successor route going away. You know, when that gets detected, boom, the feasible successor goes in. Applications will not typically notice it all. You'd have to have a pretty special application to notice a successor route dropping when there is a feasible successor available, right? And we do this off of that feasible distance, right? So on R4, getting to this network off of R1, he has a feasible distance through R2 of 11K, right? 1 plus 5 plus 5. He has a feasible distance through R3 of 13K, 1 plus 6 plus 6. So this means that R2 is going to, this path through R2 is going to be my successor. And this path through R3 is my feasible successor, which means if I lost that prefix 10.1.1.0 via R2, I don't have to do anything to reconverge my routing table. I take it directly from the topology table and install it. Make sense? We can kind of see this. I don't have any redundancy really built up in here. However, if I did show IP EIGRP topology, and maybe I do the 1.1.1.1 network, right? You can kind of see what the metric is. And you can see that it is flagged as a successor. You can see what the feasible distance to it is. If I had a more complex topology, I could also have feasible successors in here. Hopefully that makes some sense. Let me just check. Yeah, no questions. I think we're still doing okay. So let's also talk about something called the feasibility condition. Why do we care about these things like reported distances and feasible distances and successors and feasible successors? We care about them because it's kind of central to how EIGRP installs and utilizes routes, okay? So the feasibility condition kind of states that in order to even be a feasible successor route, the reported distance of the route must be less than or equal to the feasible distance of the successor route, right? So let's take a look at this. I've got a similar network to what we just saw. I just added in a third path through an R3. And from R5's perspective, trying to get to this 10.1.1.0 network, right? Well, the reported distance to that network on R2, or sorry, on R5 via R2 would be 6K. The feasible distance would be 11K. It turns out this is going to be the best route, so it becomes the successor. On R4, the path via R4, right? The reported distance on R5 through R4 is 7K, right? 1K plus 6K. The feasible distance is 13K, 1K plus 6K plus 6K. Is the reported distance 7K less than the feasible distance of the successor route? Is 7K less than 11K? Yes, it is. Well, then I'm good, right? I can set that up as a feasible successor. But what about this path through R3? Well, the reported distance on R5 through R3 is 17K, 1K plus 16K. And the feasible distance would be 33K. This is not installed. It's not installed because it does not meet the feasibility condition, right? The reported distance, 17K, is not less than or equal to the feasible distance of the successor route. 17K is not less than or equal to 11K. So I don't even use that route. It doesn't go into the topology table at all. It's like it doesn't exist from EIGRP's perspective. You might wonder, can I ever use that? Well, keep that question in mind because the answer is going to be yes. but it'll take a bit to get there. Let's talk about variance, because now we can take all of these concepts, reported distance, reported distance, feasible distance, feasibility conditions, successors, etc., and put them into a EIGRP only feature. And that is variance. Variance is effectively the ability to do unequal cost load balancing. So you can see my bandwidth on all of these is 100, except this link between these two routers, which is half the bandwidth at 50, right? So remember that we only care about minimum bandwidth, not total bandwidth along a path, right? If you were in a data center that had a lot of layer 3 links and they're all at 10 gig, but then I have 100 meg link in between 2 points, I'll pretty much never take that path, because it doesn't care that I've got a bunch of 100 gig links or 10 gig links. It just looks at the 100 meg link, right? It says, well, that's the minimum bandwidth. So what if I said, yeah, this bandwidth isn't great, but I'd still like to use that path. I'm still paying for that link. I'd like to use it. Well, variance could do that. You could also do it manually. You could just tweak. You could just manually set the bandwidth to be 100. There could be a lot of challenges or problems if you do that. I'm not a fan of changing bandwidth. I think the bandwidth should be what is the representative bandwidth of the circuit, because it makes things like QoS policy much more accurate to configure. But you could do that. But this is a way to do it natively through the EIGRP routing protocol and use it, right? So basically, as long as you meet the feasibility condition, you can create variance, and you can set a multiplier, what we sometimes call a scalar or a coefficient. And if you set the variance at 2, it basically will double the metric and of the successor route, and it'll say if I take the feasible successor, so it has to meet the feasibility condition because it has to be a feasible successor, but it'll take the metric of, or the cost of the feasible successor, multiply it by the variance factor, in this case 2, so multiply it by 2, and if it's equal to the successor route, all of a sudden I'll have 2 successors instead of a feasible successor, right? And I'll take that secondary path. Any questions on that? I don't see variance used a lot. I have seen it used a couple of times. It's a very unique feature to EIGRP. So, and it really relies on those concepts of, reported distance and feasible distance, etc. Okay, looks good. Now let's talk about the query process and queries in general, right? So what does happen if I lose paths and I have routes, but they don't meet the feasibility condition? Well, I've already told you, if you don't meet the feasibility condition, you can't become a feasible successor. If you can't become a feasible successor, you don't go into the topology table, right? So if I have a valid path like we did through R4, or sorry, through R3, however, it didn't meet the feasibility condition, if I lost R2 and R4, I could still take the path through R3, but I have to send out queries. Remember that dual algorithm that was helping us converge real fast? Well, what does it do? Well, it takes and it sends my changes, my routing table changes, like an addition or a withdrawal from the routing table, and broadcasts it out every EIGRP interface, and then every neighbor broadcasts it out every interface, and then every neighbor broadcasts it out every interface, right? Which does lead to very fast convergence. We're going to do something similar to that for queries. I'm going to send queries out all of my interfaces, and then those routers are going to send queries out of all of their interfaces, right? And what's worse is when I send those queries, I will not install a route until I get a response. When I send those queries, I mark the prefix I'm querying for, in this case 10.1.1.0/24. I mark it in what we call active state, which means I'm actively looking for a path to get there. So active state is bad. I wait until I get a response from all those queries. I wait until I get a response from all those queries before I take it out of active state and install it. However, that means even if I don't meet the feasibility condition and I can't become a feasible successor, if I lose the route through R2 and I lose the route through R4, I can send the queries. R2 comes back and says it can't get there. R4 comes back and says it can't get there. R3 comes back and says I can get there. R1 comes back and says to R3 it can get there. Okay, I have a viable path. I will go ahead and make that the new successor route. And it will change this table, right? So obviously the R2 and R4 kind of went away. So this table becomes kind of simplified. It's only got a path through R3, but it will become the successor route, right? So if, by the way, something is not responding to those queries, but not timing them out or something like that, then you can see in your syslogs, you'll see something called a stuck and active. This means that EIGRP is not installing a route because it can't determine all the different paths that might exist, and it puts it in a stuck and active state, meaning it's been active without a response for too long, and it's just going to leave it in there, right? It's just going to wait until someone responds, and you'll get these syslogs that come up that say stuck and active. So keep that in mind, right? Pardon me. Well, I mentioned this query process. It looks reasonable here. Well, let's come up with a more complex network, right? I mean, this is probably a ridiculously complex network for only having 9 routers. I sure have them connected in some pretty weird ways, but it demonstrates that query flooding process, right? And keep in mind, if I lost a network off of R1, R1 maybe has a bunch of VLANs hanging off of it, and one VLAN goes down. When R2 detects that loss, it sends out queries. Let's say it didn't have a feasible successor, so it sends out queries. Those queries bounce everywhere. It's trying to get a path to R1, right? But that query, because it's a broadcaster, basically it's a distance vector like behavior. Those queries are pervasive. They go everywhere. R4 starts querying R5 for routes up on R1. Why would it go to R5, you would say? And R5 starts querying R6 and R7, and R7 queries R6 and R8, right? And R9, actually, right? And R8 is querying R7 and R9. You can see how this makes scalability a real challenge in EIGRP. This is why I said if you're going to scale EIGRP up, beyond, say, a few dozen routers, then I recommend finding ways to bound your queries. There's really only 2 ways I typically like to bound queries, and that's through summarization or stub routing. You can also bound queries through multiple EIGRP autonomous systems. To do that, you're going to have to redistribute EIGRP into EIGRP, and now you're into that weird administrative distance challenge that I don't care for, but it is possible. There are other ways to bound queries as well. I have a link in the slides here. That's a nice blog article that you can read through and kind of learn other ways to bound queries as well. But to let you know, if you do turn on summarization, basically when you send the query, the router says, okay, I'm summarizing these networks. Is that thing you're querying for, is it in my summarized range? No. Okay, just respond back. Yep, I don't have it, right? Stub routing is a little bit different. Stub routing cannot be used if you've got a transit type of router. You can't make R5 a stub because you have routers behind R5. However, you could make R8 and R9 stubs because there is nothing behind R8 and R9, right? Well, you'd have to take that link between R8 and R9 out, I suppose. But then you could make those stubs. Stubs, when they form the adjacency, actually tell their neighbors, hey, don't query me for anything I didn't send you that I own, right? I don't know how to get to anything but my own stuff. So don't query me for anything other than my own stuff, right? Just don't even send me the query. So they behave a little bit differently. Any questions? Nope. Okay. So like I said, this means that basically we're building hierarchical networks, very similar to what we would do in OSPF, right? OSPF kind of enforces that, even if you only have 2 routers, you still have to set up your areas and you have to set up your ABR, and if you're going to redistribute routes, you have to set up your ASBR. It's a little more complex and it's a lot slower, probably 10 times slower out of the gate. Not that you can't make OSPF fast, you can, but it is slower. If I'm going to scale it out, then I'm looking at things like query boundaries, and I'm going to build hierarchical networks. And then you have a question, well, should you have just looked at a link state protocol to begin with? And I can't really answer that. It depends on your network and your preferences and your company, right? If you're very comfortable with EIGRP and you like some of the advantages and you have a lot of investment in it, then it's not worth probably going to OSPF. It's probably worth it to just properly design EIGRP to properly bound those queries, right? This is a good example of where you could use stub networking, right? I can make all of these, if I got a hub and spoke sort of topology, I can make all these spokes stubs, and then the hub doesn't ever need to query the stubs. It just doesn't even send the queries. And now my query boundary is really small. It's just going between these 2 hubs. The hubs probably have some back-end communication if they're data centers or something like that, right? But now I am designing things kind of hierarchically, which maybe we should be doing from the get-go. That's kind of a design question. But I think you see where we're going with that. We're getting close to kind of wrapping up here. We're in the last couple of sections. We're going to talk about one of the newer advances in EIGRP, which is named EIGRP. So if you keep in mind that the algorithm I gave you, right? I said it's 10 to the 7th divided by the minimum bandwidth. Well, what is 10 to the 7th? That's basically 10 gigabits, right? What do I do if I have links faster than 10 gigabits? Well, in classical EIGRP, sometimes it's also called numbered EIGRP. I prefer the term classic. I can't. Anything over 10 gig is treated as 10 gig because I can't go beyond. My metric is only so wide, right? There's only so wide a metric space, and that is 10 gigabits. And so I'm kind of stuck with this, right? Classical EIGRP cannot scale beyond a 10 gig link. And that was really the initial, my understanding is that was the initial driver for named EIGRP. And it happened in data centers when I had 10 gig ether channels, right? So that I might get 20 gig or even 40 gig worth of bandwidth before I had 40 gig interfaces, of course, right? If I had like a layer 3 ether channel or something like that, how do I deal with that? Because in classical EIGRP, I just couldn't. If I had a 20 gig link and a 10 gig link, they were just 2 10 gig links and I load share them, right? So named EIGRP was invented. They added this thing called wide metrics, right? Which scaled the bandwidth, the reference, but we call this 10 to the 7th number. We call that sometimes the reference bandwidth. And we scaled it out from 10 gigabits to over 4 terabits per second. Now, I'm going to have a link, I think, in the next slide or two, which takes you into the real math that goes into named EIGRP you're never really going to get that 4 terabits, not just because we really don't have that kind of bandwidth on our interfaces or anything, but there's other limitations on the router that are not going to allow you to get to a metric that can really scale up to that. Mathematically, it works out, but system-wise, it does not. That being said, though, I can go beyond 10 gigabits, and that's what you should take away. By the way, you might ask yourself, how do I go from classic to named? I might be in an environment that already is running classic. How do I switch to named? It's really easy. Actually, they make it very easy. It's just a single command under the routing process, EIGRP upgrades-CLI, and then whatever name I want to use. Let's convert one of my routers. Let's convert R2 here to named EIGRP. I would just come in, I go into my routing process. Oops, I have to type it first properly. Right, and it's just upgrade. And then I have to give it a name. We'll name it Scug. My question mark, you see that's it. It says, are you sure you want to do this? You say yes, and it's done. Now let's look at my EIGRP. And you can see now instead of saying router EIGRP 100, it says router EIGRP Scug, right? And it's got some other things it says as well. We'll talk about those in the upcoming slides. Oh, how many devices make us consider a network large for you? That's a great question, Mike. How big is big when it comes to scaling out EIGRP? So there is no hard and fast rule. You can't say, hey, it's great for 36 routers, but at router 37, you're done. Because there's more than just the number of routers. However, you can easily go to several dozen routers pretty safely, right? I would say between 50 and 70 routers without doing anything crazy like a lot of query binding. You could probably do that just fine. Could you come up with a use case where it wouldn't work out? Yeah, you could. If all of those routers are taking full internet routes and they're all redistributing 1 million routes into EIGRP or something like that, yeah, you're going to have problems, right? But those are corner cases. However, if it was my network, once I got to about, let's say 30 routers, I probably am going to start thinking like, oh, you know what? Maybe I want to think about redesigning EIGRP. I'd rather do it ahead of schedule than after schedule, right? I'd rather not have to react to something when it becomes an issue. I'd rather say, you know what? We started as a little 10-site company, and then we grew to like 18 sites, and then we bought 2 other companies, and now we're at 30 sites. Everything's just running fine. We're not having any problems. However, what happens when we buy a couple more sites and all of a sudden I'm at 70 sites, right? Maybe I'm working for a retail location or something and I'm starting to expand. So when I got to about 30 routers, I would probably start looking at redesigning EIGRP and start planning that process out, because things like query boundaries may require me to change topologies a little bit, or it may involve some outage windows or something like that. So that's a great question, Mike. But I would think you could easily get to 50 routers in most scenarios and not have EIGRP melt down on you, generally speaking. However, once I got to 30, I'd probably proactively start rethinking about designing EIGRP to utilize either summaries or stub networks. Hope that answers your question, Mike. So one thing I should have mentioned is when you do this conversion from classic to named that we just did, it doesn't even drop the neighbor relationship. There is no outage, okay? There's a caveat to that. There's caveats to almost everything, right? I like to tell my internal, folks, um, every rule I give you can be broken. You just have a good reason to break it, right? So, um, the big caveat to outages when you convert from classical to named EIGRP is if you had configuration in named EIGRP that happens under the interface, things like the summary configuration, it does not carry the interface level down to the protocol. Everything in named EIGRP happens under the protocol level. Everything under classical EIGRP happens part of it under the interface and part of it under the protocol level. That those items that happen under the interface, like summarization, will not migrate down. There's another question. Do we have to convert to named everywhere at once? And that's a great question. And the answer is no. And actually, we can see that. If I come back to my lab, right, and we do maybe a show IP EIGRP neighbor, you can see my neighbor has been up and stable for 32 minutes, right? I didn't even lose my neighbor. And if I come over here and I do a show IP route EIGRP, you can see I still have all of my routes, and I'm not running named EIGRP over here. If I do a show run pipe dissection EIGRP, I am still EIGRP 100 over here, but I'm named EIGRP over here. So it's a good question. So we don't have to do this everywhere at once. I can pick and choose. By the way, from an operation standpoint, I typically would say, I would recommend start at the edge and work your way in, end at the cores or at the center of your network. I would start, if you were going to go from classical to named EIGRP, I'd start out at the edge and then work my way in. There are some caveats though. If you want to have named and classical EIGRP working together side by side, then you cannot take advantage of some of the cool features within named, right? You'd have to do that after everyone got converted from classical to named. What are some of those cool features that we could get? Well, I've already mentioned we're going to double the metric space, right? We have to do that to get beyond that bandwidth limit. So by default, classical EIGRP, by the way, is a 32-bit wide metric, and named EIGRP is a 64-bit wide metric. I literally double the address space. That means that my cost can go to twice the value, right? Just kind of keep that in mind. If I take advantage of that, then I'm going to have problems, right? The local router could be aware of that, but the neighbors cannot. I can't send a 64-bit wide metric to a 32-bit wide routing protocol. So they did add, remember we talked about the 5K values, they added a 6K value called jitter or energy. Just like I recommend you don't use K2, K4, and K5, I also recommend that you do not use K6, not least of which is that even Cisco doesn't have a good use case for this. I don't know why they decided to add a 6K value when they already only used 2 of the 5K values, other than to say, I think that they were like, at least it gives us an option if later on we come up with some good reason. I think you could see where their mind was at. Named EIGRP has been out for over 10 years. I think their mind, because they call it one of the names, it has 2 names, jitter or energy. Jitter, right away, you start thinking of voice and video because jitter is a term that means something very specific in those environments. So I think that they were going along the lines of, we may at some point want to enable features or some kind of QoS features within the routing process, would be my guess, right? Remember that I mentioned it took and made all the configuration got made under the routing process, nothing under the interface anymore. Remember, I gave you that caveat that anything that was configured under the interface needs to be manually moved under the routing process, namely route summarization. And then it added address family support, very similar to what we get in, say, like BGP, for example, right? We have address families in BGP. So you get the same thing now in EIGRP, which makes it much more scalable and friendly. Does this sound a little overwhelming to you? It might. And believe me, it is. I have linked here a blog article. It is really well written. If you are really interested in understanding kind of the complexity of what happens when you go to wide metrics and why even going to wide metrics, you still might not be able to use the full capability of those metrics, that 64-bit wide address space, you can go read, when I send out the slides, you can go read about kind of the mathematical reasons why you still don't get all the features. And it isn't an EIGRP limitation. It's really a router iOS limitation, right? Or limitations, depending on what features you're trying to use. It is a really good article. I will warn you, it's going to go into some math, right? If you're extra geeky like me, you kind of love seeing the math behind some of these things. If you're not extra geeky like me, you should feel fully free not to worry about it. By the way, there are some other advantages to EIGRP. As we already mentioned, the centralized configuration. The fact that I can now do multi-protocol support via address families. We touched on this on the last one, but I do want to kind of click in there. In the past, if I use classic EIGRP and I do both IPv4 and IPv6, I literally have to have different routing processes, different EIGRP routing processes, one for v4 and one for v6. Now I could set them up as separate address families under a single unified process. Much more simplified configuration. Auto tagging support. Yeah. So what is auto tagging support? One of my customers who saw the flyer for this said, "Oh, please mention auto tagging support." And then he kind of explained to me why. And I thought, oh, that is a pretty cool use case. You can say, hey, I'm going to auto tag all my EIGRP routes with some route tag, right? Tag 10 or something like that. Tag 64512. I don't know. You know, a tag is just a number that you put on the route itself that then upstream you can set a policy against that tag. So let's say I've got EIGRP running in my campus and BGP running out at the edge, or some other routing process, OSPF, BGP, doesn't matter. And I want a routing process that says, hey, all of my tagged routes, or all my desire is all of my native EIGRP routes, I want to redistribute into BGP. But if it's not a native EIGRP route, I don't want it going into BGP, right? Well, you can do this with auto tagging, because I could auto tag all my native EIGRP routes with some value, say 10, and then when I redistribute EIGRP into BGP, I could say only allow those routes that have route tag 10 on them, so that if I have other non-native EIGRP routes, they don't go into BGP. That is a pretty cool feature, I got to admit, auto tagging. Also, the authentication goes up from MD5 to SHA-based, so a little more advanced encryption and authentication if you're going to do that in your routing. So let's talk about quick conclusion. What did we learn, right? What are your takeaways from this? Well, we now know EIGRP, it is strictly a distance vector protocol. That nonsense about it being a hybrid protocol, I understand why they went with it. It does have enhancements, but be aware it really is just a distance vector protocol, and it comes with all the pros and cons of a distance vector protocol. That dual algorithm, the diffusing update algorithm, makes EIGRP about the fastest protocol you could ever use. You don't get any faster than EIGRP for convergence. Remember that EIGRP can be simple, but at the expense of scalability, and that you can scale at it, but at the expense of simplicity. I like to think of scalability and simplicity as being two sides of a scale. And the more weight you put on one, the more you lose of the other, right? You want extreme simplicity, then you're not going to get a lot of scalability. You want a lot of scalability, then you're not going to get much simplicity. But that doesn't mean it's not scalable. It is scalable. There are definitely networks that have hundreds or even thousands of routers in them that run EIGRP natively, and it runs just fine. Remember that scalability is done mainly via query boundaries. Those queries auto-propagating is the real challenge with scalability, right? So that when I have network changes, it does cause these problems with query changes. In fact, EIGRP can end up chewing up a lot of bandwidth, megabits and megabits worth of bandwidth, if you're not careful with those queries. And so we want to set up query boundaries if we're going to scale out of EIGRP. If you want to engineer traffic to take a certain path, I recommend using offset lists, particularly if you want to do it for certain prefixes, right? That's really your only reasonable option, not your only option, but your only reasonable option to me. You could use delay if you want to affect everything a little bit. You could use bandwidth if you like the all nuclear option. I'm not a fan of tweaking bandwidth for more reasons than just the EIGRP math, but if you really want to, you can do it. If you're really going to use EIGRP and make EIGRP work for you the way it should, you really want to take the time to understand concepts like distance, feasibility, and path selection. That's where we spent a lot of time on this talk. So hopefully you got something out of that. And, if I was going to be deploying EIGRP in a green field today, I'd probably do named EIGRP. Why even start with classical EIGRP? I would go straight to named. If, however, you're in a brownfield environment, be aware that named EIGRP allows you to scale up beyond that 10 gig limit and also gives you advanced features. So maybe consider, does it make sense for you to move to named EIGRP? Now, if you're in that real simple use case and you don't really need address families and you're not really doing network summarization and you don't have any, links above 10 gigabit, maybe named EIGRP doesn't really buy you much, right? If you're not in that kind of a network, then maybe you want to consider doing it. And remember, you can start out at the edge and then slowly work your way into your core or your data center or the center of your network, whatever you want to think of it as, right? You don't have to do this everywhere at once. Now, I'm not going to go through these, but when I send out the slides, you can do this, you cannot, but you'll see I've got a whole bunch of questions for you. Looks like I didn't number them properly, so I'll renumber them. I think there's about 15 total. That's your homework, but it's optional homework. It's not like I'm grading it, so do it or don't do it. That's kind of up to you. But that's about it for today. I didn't see any other questions come up. If you do have any questions, go ahead and throw your hand up. Okay, I don't see anything. One quick housekeeping thing I probably should have put up at the beginning. I'm coming up with the March topic. It was originally going to be Meraki. However, Cisco asked if they could do Meraki in April because there's a big Meraki release coming in March, and they wanted to wait for that to come out to see if their capture the flag environment could get updated. So we'll probably do Meraki in April, and I'll probably do a different topic in March. I might do another routing protocol. I'm a old school routing person, so I do routing all the time. However, maybe we'll pick something else. Maybe look at SD-WAN, or maybe I could get someone to talk to us about QoS, some other probably enterprise network type topic. If you have suggestions or thoughts on that, please, like I said, feel free to email me. That being said, we'll wrap up for today. I'll stop the recording.
Need help? Call our cybersecurity team and book a consultation with us today.